My name is Thomas Beckers. I am a postdoc at the University of Pennsylvania, and today I want to present our paper, Learning Rigidity-based Blocking Control Using Gaussian Processes with Probabilistic Stability Guarantees. And this is joint work with George Pappas and Leonardo Colombo. So the motivation of this work is basically that nowadays we have an increasing amount of applications that use swarms of robots. For example, in search and rescue scenarios, for area mapping services, but also to establish a temporal communication network or even for light shows. And what we typically want to do is to control the agents to specific formation with flocking behavior. And this raises many challenges. For example, there might be the need of decentralized communication since there's no communication between the agents and the central authority possible. Further, we want to have some stability and performance guarantees for the closed loop. And finally, the agents might have heterogeneous dynamics due to, for example, different kind of agents, or in case of the same kind of agents, there might be some variations in the manufacturing process, and therefore we might have slightly different dynamics of the agent. And in this work, we focus on how to handle this unknown dynamics of the agents. So the problem setting is as follows. We consider here n agents in a 2- or 3-dimensional space, and the agent I, we have the position pi and the velocity vi and an external input ui. The system is, or each agent is modeled as a double-integrator dynamics. And now assume we have some additional state-dependent unknown function fi. So f is individual for each agent. And the source of f here, of this state-dependent function, can be, for example, unmodeled dynamics, like friction in the system, but also external forces, like a state-dependent wind field for drones or currents. And furthermore, we assume that there's no communication between the agents possible, but the agents can measure the distance to neighbors defined by some graph structure. So the goal is now to find a decentralized controller such that the agents converge to a desired formation with consensus in the velocities. Okay. Let me give you some more details on the graph structure. So we work here with a framework, and which is an undirected graph. The nodes are the agents, and the edges are the distances between the agents. And for the latter controller, we introduce the following definitions. So the Euclidean distance between two agents pi and pj is denoted by zk. The rigidity r of z describes basically the stiffness of the structure. That means the variation of the distances when we move one of the agents. And finally, the desired formation S, defined by a set of desired distances dk. So the goal is to find a decentralized controller such that the formation error ek converge to 0. And this error is the error between the actual distance between the agents and the desired distance dk. And we also want to see a consensus in the velocities. So we have here the assumption for the desired formation, that we assume that this is a minimally infinitesimally rigid framework. So let me show you some example to as explanation. So on the left side, you see a framework which is not rigid because we can move some of the agents without changing the distance. In the middle, this is a rigid framework since we cannot move one of the agents without changing the distances. And on the right side, we have two more properties to get a minimally infinitesimally rigid framework. So first, in this case, if we remove one of the edges, the framework is not rigid anymore. And second, when we move one of the agents, there's not even an infinitesimally change in the structure of the graph. So that means that the only motion over the agents in the desired shape are the ones defining a rotation or translation of the whole desired shape. So if we move one of the agents, we would move all the agents so that we keep the desired shape. And in this case, the rigidity matrix R has full row rank. Okay, now going back to our double-integrator dynamics of the system. For this double-integrator dynamics, Diggert et al. Proposed a decentralized controller which uses velocity feedback and a position feedback. And the velocity is weighted with the Laplacian or with calligraphic L, and calligraphic A is constructed with the Laplacian matrix. And this is a block diagonal matrix. And the position feedback, or the position error E, is weighted by the rigidity matrix R. So this controller guarantees local exponential stability of the desired shape S with flocking behavior, which means we have alignment, cohesion, and separation of the agent. So, but this result only holds in case of a double-integrator dynamic. So if we have this additional unknown force F here, we have no guarantees anymore. So how can we deal with this unknown dynamics F? And what we propose is a learning-based controller to overcome these unknown dynamics in the system. And since there's no communication allowed between the agents, each agent collects its own data set. So the agent I collects the data set calligraphic DI, and this data set consists of the position of the agent PI and the velocity of the agent BI for some times T1 to Tm, and also on Yi, and Yi is basically the acceleration of the this agent minus the control input Ui. And this measurement, like the acceleration, is typically noisy, and therefore we allow that this measurement can be corrupted by some Gaussian noise. So, and since we're using an online learning method, we allow that this data set can be updated during runtime. So how does that look like? You see here on the right side, the evolution of the number of data points over time. For example, in this case, we collect data between 0 and 1 second. And then at 1 second, we update our data set. And then we have 10 data points in our data set. And we collect again 10 data points. And we update again our training data set. And then we have 20 points in our training data set. And we assume that after some time, we do not update the data set anymore. And this is a reasonable assumption because normally we have some computational and memory limits so that there's an upper limit for the number of training data. Okay, now after collecting the data, or now we have this data set, And based on this data set, we want to predict this unknown function f. And here we use a Gaussian process for this prediction. So let me introduce Gaussian processes. A Gaussian process is basically a distribution over a function space, and this distribution is fully defined by a mean function m and a covariance function k. Here on the right side, you see the prior distribution, in red the mean, in gray the uncertainty, the variance. And using Bayes' rule, we can update the prior with data to get the posterior distribution. And now with one data point here in blue, you see that the uncertainty is decreasing around this data point, and the colored lines are some samples of the Gaussian process. So with more and more data, our prediction gets more and more confident. And so at the end, for a new test input x star, we can predict the output y star. And for this prediction, so like for the posterior distribution, we get a closed form solution, and the mean is given by the covariance between this test input x star and the training input capital X times the covariance of the training input capital X plus the noise of the sensor for the acceleration times the output data capital Y. And we also get a closed form solution for the variance. Another useful property is that there's a model error bound, which means when we have an unknown function f here in green and the prediction of the Gaussian process, the mean prediction, we can upper bound the model error for over a closed set omega with a specific probability. So using this property of the Gaussian process, I want to present our main result. So we consider here the system of agents with unknown dynamics and this online learning GP approach. So we collect each agent collect data and predicts the unknown function f. And we assume that this desired formation shape S is infinitesimally and minimally rigid. And in this case, with the controller, with velocity feedback, position error feedback, and now this additional prediction of the Gaussian process, we can guarantee that the error is uniformly ultimately bounded in probability. And this bound here for the position error and the relative velocity depends on the distribution and number of the training data, and also on the probability of this bound. So if we want to have a higher probability, then we typically have a looser bound. If we want to have this bound with lower probability, this bound is tighter. Okay, so with this approach, we performed a simulation. In this case, we have 4 agents in a 3-dimensional space. And for 2 of these agents, we have an additional unknown dynamics f. So on the left side is now the case without learning. So with the standard controller, and on the right side, we use our approach where we collect data and train a Gaussian process, and then use this prediction in the controller. And the desired shape is some triangular shape. Here on the left side, you see that we have some unpredictable behavior of the agents. On the right side, you see that we converge to this desired shape and that we have a consensus and the velocities. I show it again. Here you see on the left side some unpredictable behavior due to this unknown function f, and on the right side, we converge to this shape and we have a consensus on the velocities. Okay, so I want to conclude my talk. I showed you that our approach allows an online learning-based decentralized control law. And with this control law, we can prove that we converge to a bounded set around the desired shape with flocking behavior. And since it's an online learning-based approach, the incoming data allows us to reduce the error over time. Thank you very much for listening. If you have any questions, feel free to send me an email or browse on my website, www.tbeckers.com. Thank you.